everyone. I'm gonna first would like to thank the organizers for the opportunity to talk about our work, which basically was a study the effect of the structural disorder. Thank you. Okay. So we were studying the effects of the structural disorder on the magnetic property of some geometrically frustrated magnets. I understand there are some students in the audience, so I have a couple of very basic slides here. They can profit from there. I apologize to the specialists. So I'm going. Whoops. Let's try this. Okay. I'm going to start with this very basic thing. So what I have here are spins confined to the vertical direction. And so if you think of these spins on a square geometry, it's obvious that you can minimize the first neighbor's interaction for either ferro or antiferromagnetic interactions. But when you have a triangular geometry, that's not possible anymore for antiferromagnetic interactions, right? There's always one interaction which will be unsatisfactory. So that's what we call geometrical magnetic frustration. We should differentiate this in principle from the other case of magnetic frustration where you have disorder included. Here I'm showing this example where you have mixture of different kinds of magnetic interactions present. Whenever you have geometrical frustration, you have this ground state degeneracy. So for example, for a triangle, an equilateral triangle, we have 6 non-equivalent spin configuration, but all of them with the same energy. Okay, so how to experimentally assess how frustrated the magnetic system is? The simplest way is just to measure the magnetic susceptibility. You know, you can make a very simple model, mean field model for the paramagnetic susceptibility, and then you have this famous Coulomb law where the inverse of susceptibility has a linear behavior with temperature, and there is this Coulomb temperature here, which sets the scale for the magnetic interaction. So we should see magnetic long-range order at the temperature more or less similar to the Coulomb temperature. That's what happens for normal magnets, and that's not the case for frustrated magnets, right? Because of the degenerate ground state and the frustration, the susceptibility continues following this law, even below the energy scale of the interaction. And eventually, the system will order at very low temperatures. So you can just use this ratio between these two temperatures, the Coulomb temperature and the temperature where you eventually see the long-range magnetic order, to define this frustration index. And in this way, that's the simplest way to characterize how frustrated the system is. Okay, but I was talking about the triangular lattice. You have in nature, and you can make in the lab, several systems based on these units. We have already seen here the Coulomb lattice, and in 3 dimensions, we have also FCC lattice, edge sharing, tetrahedra. The equivalent of this unit is this one, the tetrahedra. At 3D, and also the Pyrochlore Lattice, which I will be focusing on, which are lattice with corner sharing tetrahedra. Okay, so here again is the Pyrochlore Lattice. Usually when you have this stoichiometry, materials with this chemical formula A2B2O7, they tend to fall in this Pyrochlore family of structure, which are shown here. So this is just the A and B lattice. I'm showing in the different drawings the oxygen position. There are 2 inequivalent oxygen positions in the Pyrochlore lattice. I'm showing them here, the green one and this orange. So, and here are some of the examples of materials you can make on this family, the Pyrochlore family. You basically need these metals with valence 3 plus and 4 plus. So these are the materials you can try to add together to make compounds of this family. Very well. So focusing on the most famous one is the titanates, where we use for B, titanium. One of the very important things on the physics of pyrochlores is the magnetic anisotropy, which comes from the crystal electric field basically related to the oxygens, which has the high electronegativity. So we have these two that I said before, oxygens, non-equivalent positions, 48F and 8B, the green one and orange one. And depending on the rare earth you have on your sample, you might see different magnetic anisotropy. For in the case of gadolinium, the situation is more or less isotropic, so we have Heisenberg spins. So I failed to mention that I'm only dealing with one magnetic ion here in the structure, right? We had this A and B, but of course, titanium 4 plus is not magnetic. So let's go back again. Okay, so here's the magnetic lattice. I'm just showing 2 tetrahedra. And then for gadolinium, you have a isotropic situation, but for terbium, holmium, and dysprosium, we have this huge anisotropy, single anisotropy, which for this central spin, it's along this direction. That's what we call the local 1-1-1 direction. So each tetrahedra has a 1-1-1 direction which connects the vertices to the center of each tetrahedra, right? So for this spin, that's the direction for the anisotropy. To that one, it's something like this, and that one this, and that one like this way. So they behave like Eisen spins. And in the case of erbium and ytterbium, we have a situation where the anisotropy is more XY type, right? There is also a component along the 1-1-1 direction, but mainly it's the XY local plane, which is perpendicular to the 1-1-1 direction. Okay, that's what happened for erbium and ytterbium. Right, so one of the very famous pyrochlores studied for a long time now is the famous spin ice. So it's just the holmium and the dysprosium, rare earth. And what happened in this system is that you have a very strong anisotropy, as I said before, along the 1-1-1 local direction, and ferromagnetic interaction. Actually, the exchange interaction between spins is antiferromagnetic, but you have a huge dipolar interaction between spins. So when you sum these two things, you end up with ferromagnetic interaction. And because of the anisotropy, it's funny because the anisotropy changes things around. Usually, we are used to see frustration for antiferromagnetic interaction, but here, you see, because the spins are confined to this 1-1-1 direction, if the interaction is antiferromagnetic, you have a non-frustrated situation, right? It's always possible to point all the spins pointing inwards and all the spins pointing outwards from each tetrahedron, and everybody will be happy. But in the case of the ferromagnetic interaction, where you need one spin pointing in and one spin pointing out for each pair of spins you choose on the tetrahedron, then you see that's impossible to do that for all the pairwise interaction. The best thing you can end up is this two pointing, I keep pressing the wrong button, two pointing in and two pointing out, which was known by the 2-in, 2-out ice rules. That's because there is an equivalence here with the ice water. So in the ice water, you have always two hydrogens close by to the oxygen and two far away. So it's a very similar situation. The hexagonal lattice of the ice, that's one of the structures. It's very well defined, but the protons position on this structure is not unique. So there's again frustration here. This was pointed out in 1997, and this analogy became even more strong when people measured the presence of a residual entropy for the magnetic material, which is in very good agreement with the residual entropy observed in water ice. So what we do to estimate the residual entropy is just to measure the specific heat from two temperatures. You know that at high temperature, you have an Ising system for the dispersion in Homeu, so you expect two states. So at high temperature, the entropy should be RLN2. And then you measure the variation of the entropy by integrating the specific heat, the magnetic contribution to the specific heat over T. That's what I'm showing here. And when you do that, if you subtract RLN2, what you get, this number here would be the entropy at very low temperatures associated with this system. And this was estimated very long time ago by Pauling in the 30s. He basically treated each tetrahedron independently and just compute how many configurations you would have in this way. And you see that there's a very good agreement here for these two data. Okay, from the theoretical point of view, one of the first models to understand the spin ice was this so-called dipolar spin ice model, where you take into account first neighbors only on the Hamiltonian, and then this dipolar term, since again, it's a very strong, each one of these ions, dispersion in Homeu has a very huge magnetic moment, about 10 Bohr magneton. So with this model, we were able to describe the data specific heat and also neutron scattering. Right, here's the theory based on this Hamiltonian, and that's the experimental data. Neutron scattering along the 001 plane. Later on, people improved the models and included interaction going further up to the third nearest neighbors, which improved this agreement between these two results. Okay, another interesting thing on the spin ice is related to the elementary excitation at very low temperatures. So they are basically associated with the flip of a single spin. I'm showing here what would be the ground state, this 2-in, 2-out ground state. If you flip the center spin here, what you get is something analogous to a monopole pair creation, right? Because you have here the magnetic charge is 0. When you do that, you create a magnetic charge here and one with the opposite sign over there. And the interesting thing on the Pyrochlore lattice, because of the frustration, is that you can move apart these two monopoles with a finite energy cost. They will interact through this magnetic Coulomb interaction. So suppose you flip this spin over here and create these two pairs here. If you flip this spin, you restore the magnetic neutrality of this tetrahedron, and this magnetic charge will move here, and then you flip this spin, the magnetic charge will move here, and you flip this spin, and so on. So these quasi-particles, magnetic monopoles, are connected by these Dirac strings. And the dynamics at low temperatures are associated with the movement creation and movement of these magnetic monopoles. Very recently, people have seen cooperative and memory effects on the spin dynamics at very low temperatures, even with the absence of disorder in the spin ice materials. So here's an example for the this spin dynamics I'm talking about, and it's being adjusted to this Vogel-Fokker law, a phenomenological law used for glasses, spin glasses. Say again? That one is Mosner paper. I think, I'm not sure if he's on this one. That one is over here. I'm not sure if he's among the authors here, but he's definitely, I think he's in this PNAS paper here. Okay, so what we'll be talking today here is what we did on this, focusing on these two rare earths, the terbium and E-terbium. I'm going to say TB and YB to avoid confusion. So what we did, so first let me introduce this YB compound, YB2 titanium 207. We've known this material for over 50 years, but only recently we have a better understanding of the physics behind it. At first, this was thought as a very good candidate for spin liquid physics. People have seen continuous spin excitation in neutron scattering, which condense into spin waves for very small applied magnetic fields. And most of the neutron results on these materials fail to see long-range magnetic order at zero field. There was also very extreme sensitivity to small amounts of disorder on the material. I'm showing here an example of this that specific heat data showing that polycrystalline sample has more sharp and defined peaks associated with phase transitions than single crystals. Later on, people start to understand how to grow single crystal property of this material. And nowadays, we understand how to describe this system. It's through this Hamiltonian, which involves a very high anisotropic exchange matrix. So on this matrix, we have J1, which is the exchange constant associated with the XY plane. That's a planar exchange. The J2 is the uniaxial easing coupling along the 1-1-1 direction. And then you have the J3, which is the symmetric off-diagonal terms, and J4, antisymmetric Zagostinski-Moria type of interaction. So here I'm showing a phase diagram based on this Hamiltonian. That's for J3 negative and J4 equal to 0. I cannot show in a two-dimension something with 4 components. And you can see here that the YB compound, it's at the very edge of a ferromagnetic phase surrounded by 3 different antiferromagnetic phases, C2, 3, and 4, which I'm showing here on the other side. The ferromagnetic phase is not a collinear ferromagnet, it's a splayed ferromagnet. There is a small angle here, about 5 degrees between spins, and the transition temperature is of the order of 260 millikelvin. Very recently, people have realized that this ground state, this ferromagnetic ground state, is not homogeneous. You have some antiferromagnetic regions separating ferromagnetic ones, like here. So people are talking about the spin texture in the material. So here we have some ferromagnetic in the vertical direction, pointing up. And then there is an antiferromagnetic C3 domain boundary connecting these 2 regions, one pointing down and the other one pointing up. Say again. It's a kind of domain wall because most of the sample is in the ferromagnetic state. So it's a small region separated them. If the what? No, I don't have it here with me now, on top of my head. I'm not sure if it's being measured quantitatively. But that's a good thing. There's a big discussion in this paper. Actually, this came from, I believe, this one. There's a big discussion here on this paper on why they think there is this. They have some signatures of this antiferromagnetic state on the sample. Newton scattering. Newton scattering. Yes. Okay, so turning to our work now, what we did, we tried to explore this phase diagram here, making small change on the structure to see if we can assess these other phases, antiferromagnetic ones, by replacing titanium by zirconium, right? So zirconium is close by to titanium. It's a little bit smaller, bigger. And then this in some way is similar to putting a chemical, that's what we call chemical pressure on the material. So we thought we could perhaps control the magnetic interaction by doing this substitution, titanium by zirconium. So we made samples using both the regular solid state method, which just mixing the oxides, and also using the soft chemistry method, which is very good for when you have mixture elements. The reaction happens at the molecular level, so we have a very good homogeneous samples. Here I'm showing just the electron microscopy, scanning electron microscopy data, which shows that when you have this mixed zirconium, titanium, you have increased porosity in the samples. And for the end members, I'm just showing the X equal 2 here, but they have this, they are more crystalline. Okay, so we made several samples. Here are the X-ray diffraction data, and we could detect different structures on the material. Starting on the Pyrochlore lattice for X equal to 0, we detected the fluorite, defect fluorite structure, which is similar to the pyrochlore, but just with one side for A and B, right? That's what I'm showing here. There's a 50-50% of occupation of A and B. So pyrochlore is a superstructure of this one here, the defect fluorite. And upon increasing the X value, we go to a even less symmetric and still disordered structure, this delta phase, which is a hombohedral system. So, so here's the heat value refinement of the X-ray diffraction for the pyrochlore sample. And one interesting thing we notice is that even for the samples with the structure seems to be this disordered fluorite one, where the A and B sites are mixed, it's not a homogeneous structure. If you look careful here at the diffraction, you see peaks, the superstructure peaks associated with the pyrochlore structure. That's for X equal 1. Here's in the log scale. You can clearly see. So we think there is a question of this long range and local order of the pyrochlore structure inside this fluorite matrix. This is better investigated by Raman Spectroscopy. So I'm showing here the Raman spectroscopy at room temperature for all the compositions. And you can follow, there are several peaks here associated with the active modes, active Raman modes of vibration. And this one is a particular one associated with the Pyrochlore structure, the A1G. And you can see that even for the sample, which from the X-ray diffraction seems to be in the fluoride, defect fluoride region, we still see a peak here, so there's still pyrochlore structures inside that phase. So with that, we were able to make this phase diagram. So starting from the YB titanate, going to the zirconium one, you pass to the pyrochlore, to defect fluoride, and then eventually to the delta phase. Again, you also have this question of the short range and long range on the structure. It's not a clear scenario. Now to the magnetic data. Here I'm showing the magnetization as a function of the field in the paramagnetic region at 1.2 Kelvin. You can see that there is a variation of the saturation moment. This might be related to some small change in the anisotropy of the samples depending on the composition. And here on the right, the AC susceptibility as a function of temperature at very low temperatures. And we were able to see anomalies in the AC susceptibility, which we associated with that phase transition, magnetic phase transition to long-range order. For almost all compositions besides the last one, XGO2, which we were not able to go low enough in temperature to see what happened. Okay, so here I'm showing the frustrated index, which I defined at the very beginning for all the samples. We can see that you increase the frustration on this material as you replace titanium by zirconium. I failed to mention what are these temperatures here. They are just temperature for thermal treatment of the samples just to improve the quality of the samples. So we have samples, depending on the synthesis method, sol gel or solid state reaction. And here's the peak position, which we associated with this ferromagnetic transition, which is going down as you increase disorder and gets a system which is less symmetric, which is not an unexpected result. Okay, that's the case for the YB sample. Now I'm going to talk about the TB. So terbium titanate, it's a material that has antiferromagnetic correlations. Contrary to what happened to the YB sample, we don't have much indication of sensitivity to small disorder on this sample. And this material is for a long time believed to be a very good candidate for spin liquid physics, right? There's no long range order observed for this material down to 50 millikelvin. But even with this very high Curie-Weiss temperature, 19 Kelvin. Terbium titanate. That's Ising physics. The anisotropy is more Ising. For terbium, it's comparable to dysprosium. I'd say it's big, yeah. It's like 9 Bohr magneton. So what we did here, we just we made this composition. We replaced titanium by zirconium. And in doing that, we get this defect fluoride structure You see there are less peaks here, so this is more symmetric structure than the Pyrochlore. And then we measure the AC susceptibility. And here the glassiness of the spin ice shows up. So the AC susceptibility has a peak, which depends on the frequency. We have a range of frequency here. We quantified how much the peak changes as a function of frequency, is this number here, 0.064, which is comparable to the ones observed for the titanate and also the hafnate equivalent compounds. They show it, this displacement here of this peak, very close by to the one we measured, but with one big difference, right? We are seeing this at 3 Kelvin, which is roughly 10 times higher than the temperature where they observed this kind of phenomena for these two materials. Again, this is not, does not match very well what's expected for a canonical spin glass, which would be a very smaller dependence on the peak temperature with the frequency. It's in this range here. So it's a kind of a glassy characteristic, but a real canonical spin glass. And here are some tentative to model the things with some known models for glassy system. There's dynamic scale, scaling law, the Vogel-Fuchs law, the same one used for the spin ice materials, which seems to reasonably describe the data. Also another one here, this power law of the Arrhenius behavior, which was used for the TB titanate. Sorry, here it's wrong. It's these are the parameters for the terbium titanate one. Those are the parameters for our sample. They're somehow similar. Okay, and that's it. We have made this substitution of zirconium, titanium by zirconium, and observed different structural different structures for the YB compound, changing from the Pyrochlore Lattice to this defect fluorite, and going to this even less symmetric and disordered delta phase. We saw this suppressing of the magnetic long range order with structural disorder, increased frustration with disorder, and a possible candidate for spin liquid physics for the end member YB zircon 207. We have also seen spin glass-like physics for the terbium zirconate. And also, we were able to measure considerable spin dynamics at very low temperatures for this material here, around 100 millikelvin. So that's it. Thank you.
Any questions?
Thank you for a fascinating talk. This is very interesting to me, but I didn't know about that this is all possible to measure. Fantastic work. So I have a few questions. Maybe you went a little fast and I may have missed something.
I did.
So you're saying that you can actually observe some glassy behavior even though in cases where you would not think that the disorder is strong or dominant. Is that correct?
That's the case for the spin ice materials.
For the spin ice. And
they are very clean sample. They're very, you can make huge crystals.
Yes.
Right? These are that was in my introduction, not the system that I actually studied. This one here.
Yes. And so this doesn't have any, this cannot order in a uniform way, this one. It's so frustrated that it cannot order in a uniform way at all, right?
No, there is this, the only thing you see is this 2 in, 2 out.
Right.
Local order.
Right. But the other ones are a little bit less frustrated, and that's why they can, right?
That's right.
So my question is, are these transitions all second order to the ordered phase? Or you can have examples of first order transitions?
We do have example for first order transition.
So let me
Erbium titanate, it's first order transition.
Okay. So let me tell you why this caught my attention, because I have not been involved in this spin ice work or spin glass work, but we are interested in charge ordering on frustrated lattices and in a number of families of materials, including some theta organics, which are quarter field organic materials, and also there are some transition metals like chalcogenides. They all have some phases where the ground state can be uniformly ordered, and this charge order can be the stripes or some triangular lattices, but you can melt it, and above some temperature you have a liquid. Now it turns out they are first order transitions to this ordered state, but you can supercool this by quickly cooling, and they claim that they observe some kind of structural, some kind of amorphous ordering without any substantial disorder. These materials are super clean. And there is now good kinetic evidence and also STM evidence of amorphous states being in metastable states. So in some of them, they also studied some non-equilibrium relaxations, which also look glassy. And so this has been somehow a big surprise that the electronic systems can freeze randomly without disorder. But now it seems that there is a lot of evidence, and this is in a semi-classical regime, similar to what you have now. My question is, have there been other measures of glassiness, like, for example, aging? Aging behavior is characteristic of glasses. This is what they study in spin glasses. You know, they cool it rapidly, quench it, and then they watch the relaxation depending on the waiting time. So this is one of the things I'm wondering.
I think it's, and here on this PNAS paper, there is this aging.
Oh, they also have aging?
Yes, they also have it.
Fascinating.
And now this is the paper where they're making this claim that what we have here is what we call the structural magnetic glass.
I see.
So you don't have disorder, but you do have a landscape of the potential energy, which is very complicated.
Let me take a picture of this reference.
Sure.
And what I also want to ask is yeah, I want to mention that we studied distribution of internal fields in these Coulomb glasses, both with disorder and without disorder. With disorder, they assume generally a power law form, which is called Diffraction. But what we found is that in the self-generated glass, which is very similar to this, there is actually a harder gap. So some excitations in these self-generated glasses may be actually different dynamically than in glasses which are due to disorder. So there may be some dynamical signatures of these self-generated glasses which are different than the usual spin glasses. I just want to mention this as a possibility which may be studied experimentally.
Okay. But in that case, it's charged, right?
It is charged, but you know, it turns out that if you put long-range interactions, very similar to this dipolar, then we studied classical lattice gas models, which is you have two states of charging, and so that's almost identical to Ising spins.
I see.
So these classical models are almost identical to this, so we study both triangular and pyrochlore.
I see.
And you can see very similar. Generally, it seems that this metastable states being glossy is actually much more a robust feature of frustrating systems with long-range interactions than you may guess.
Okay.
Yeah.
That's the feeling in the field.
Fantastic.
For the magnetic system also.
Very beautiful work. Thanks.
Okay, thank you.
Rafael, very nice talk. Do you see this ubiquitous linear term in the specific heat in these materials also?
No,
very low temperatures, no?
We haven't detected that. That would be expected for a canonical spin glass, right?
Yeah, and glasses also, no?
Not also canonical spin glass.
Yeah.
Any glass? Yeah, I
But
don't.
in glasses, it turns out to be at very low temperatures, below 1 degree Kelvin. So
We don't see that. You know, in the spin ice, we get this peak related to the ice rules when the spin starts following the ice rules.
you didn't
So
see
maybe
the power law at very low temperatures, you know.
No, it's not linear.
It's not linear.
No, it's not linear.
Thank you.
Any more quick question?
So for the terbium zirconate, perhaps you showed this, but I missed it. So is it clear how the low temperature behavior looks like? Is there a gap? Is there anything which you can say from specific heat or magnetization measurements? Are there low temperature magnetization measurements?
There are, but there's no feature at all For terbiums, you mean zirconate or titanate?
Ytterbium zirconate.
E-terbium zirconate. No,
Yes.
that's all we have. Where am I? I think it's. Yeah, we were at the very bottom of very limit of the lower temperature we could achieve, so we couldn't see anything.
Okay.
We don't know what happened below.
So lower temperature magnetization measurement would be in order, perhaps.
It would be, you would need a powerful, more powerful dilution fridge or nuclear demagnetization equipment. That's a paramagnetic demagnetization cryostat.
So the stoichiometric one, the x equals 2, is that available in reasonably large single crystals that one can
No.
hope for neutrons?
No, they are all powder samples.
Okay,
They're all powder samples.
thanks.
Okay, so we have to move on. So let's thank the speaker again.